Okay, we can resume. Actually, this is one of my favorite things to talk about in the whole volcanology world is what we're going to get into next, okay? So let me start off. Let's say I have a little slope right here. I did this with this book right here. If I put a drop of water on there, what's it going to do? It's going to go down, right? If I take a drop of basaltic magma, the red runny stuff you see in Hawaii, and let's say I heat this room up to like 1200 degrees, okay? Super hot, right? So that material isn't going to cool off at all. If I put it there, it's going to sit there. It's not going to move real slow, like you would expect of a viscous fluid. It's not going to move at all. It'll sit there forever. Now, if I increase the slope enough, at some point, I will get to the point where it'll start moving. And it'll actually move pretty fast because it's a pretty fluid magma. But water, the minute I put any slope on this at all, it starts to move, right? When I said before that water and magmas are really different, that's one way that they are really different. Water will flow under any stress at all, any slope. Magmas won't do that. Magmas have the ability to just sit and resist stress. We'll talk about why here in a minute. But to sort of get there, we're going to kind of go back to basic physics, talk about stress and pressure and force, get you all up to speed so that we all have the same vocabulary, and then talk about two properties that fluids have: viscosity, which you know, and yield strength, which you probably don't know. But it affects the way magmas behave in a really big way. So let's start with some terms. We have compression, tension, and shear. Compression is squishing, taking a force, applying that force over an area where you have pushing from two opposite sides. Tension is pulling apart, taking something and trying to stretch it rather than squish it. And shear is where you kind of smear something. So those are our three main kinds of stress. Rocks in general are really strong under compression. Take a rock hammer and try to break a rock. It is not easy to do. When you're hitting that rock, that's compression, right? Smashing it. If you want to break a rock, pull it apart. You can find out a way to do it. Rocks are really weak under tension. They're about 1/10 the strength is under compression. So think back to tectonics. When you have extensional areas, you get lots of breaks. Rocks are really weak when you extend them or put them under tension. They're super strong under compression. They're fairly strong under shear. When you put stress on a rock or a fluid, several different responses can take place depending on the behavior of that material in the face of stress. Stress, pressure, same thing. So when you stress something, you can get strain. Strain is the change in shape of a material in response to stress. Now you're used to rocks behaving elastically. If you put stress on a rock, it'll bend a little bit, maybe not enough for you to even notice, and then it will shatter. It will break brittly. So if I hit that rock over there hard enough, I'll chip part of it off. That's how you're used to rocks behaving. But in order to break that rock, I have to hit it with enough stress so that it exceeds the strength of the rock. If the strength is greater than the stress, then the rock won't break. It's like this pencil. I can flex this pencil, it'll bend a little bit, right? And if I keep applying that stress, it'll eventually snap. Now, if I don't break it and I bend it and then release the stress, it'll flex back into its original shape. That's what it means to be elastic. It'll bend under the stress, then it'll snap back when you release the stress. And if you stress it too much, it breaks. It shatters. You guys are pretty used to things behaving that way. Plastic refers to how material behaves when you apply the stress and it stays deformed. Think of clay. If you stress clay, you bend it or dent it, it stays dented. It doesn't snap back to its original form. Fluids behave this way. Even rocks can behave this way if you give it enough time. Grains can shift around. You've seen anticlines and synclines. That kind of shows that rocks can have this sort of dual behavior. On short time scales, if you apply a lot of stress, they bend, flex, but regain their shape. Unless you exceed the strength, then they shatter. But on long time scales, even solid rocks like the ones we have over there can behave more plastically. And we already know that stuff in the mantle behaves plastically. So plastic is where you apply a stress, the stuff deforms, it bends, and then when you release the stress, it stays deformed. Now solid rocks, like I said, deform elastically on short time scales, plastically under long time scales. Magmas behave plastically under most time scales, but even magmas can break. You can break a fluid if you strain it fast enough, and that's what happens during a volcanic explosion. That material is, think of a foam, okay? Your magma's inflated to a foam. It's got so many bubbles in it, right? It's still hot. But if you strain it quick enough, you can actually start breaking apart that little piece of foam, and that's where you get pumice from. Pumice are just broken pieces of magmatic foam that was once liquid, and it shattered in the conduit on the way to the surface. So I'm going to talk about stress and behavior in probably a way you're just not used to thinking about, because magmas are weird things. Okay, in order to do that though, we all have to have the same background in terms of physics. Most of you have had some physics, some of you haven't. Doesn't matter. We start at the beginning. What is force from physics? Force equals mass times acceleration. Remember? What unit do we use to measure mass? Kilograms or grams. What about acceleration? Acceleration is a change in velocity, right? Velocity is measured in something like meters per second. And you usually talk about a change in velocity over time. It changed by 5 meters per second every second. Acceleration is speeding up, right? So let's say it's moving 5 meters per second 1 second. The next second it's moving 10 meters per second. The next second it's moving 15 meters per second. Then 20 meters per second. What's the acceleration? It's changing by how much every second? 5 meters per second every second. So that unit becomes meters per second, or meters per second squared. So your unit of force, mass times acceleration, is kilogram times meters per second squared, which gives you kilogram meter per second squared. Physicists refer to that as a Newton. It's a measure of force. Now, usually here in geology, we talk about acceleration as being from gravity. And here on Earth, the gravitational acceleration, do you guys know the value? 9.8 meters per second squared, okay? So every second that gravity acts on an object with mass, it accelerates by 9.8 meters per second. If you're on Mars, it's 3.3 meters per second. Mars is a smaller body in terms of mass, has less gravity, its acceleration is less. Okay, so that's force. What's the difference between force and stress, or force and pressure? What's pressure? All right, think of it this way, okay? Standing here, right? Now, if it wasn't for the floor, I'd be accelerating downward, right? Throw me off an airplane, what happens? I go zooming towards the Earth, and my speed increases until eventually you hit this terminal velocity thing, which we won't talk about. But if I was in a vacuum, my speed would just keep increasing, okay? So right now, though, I have this floor preventing me from going down any farther, right? But I had a volunteer to ask you to come up here, lay on the floor, and I would stand on your head, okay? Would you feel it if I stood on your head? Would it crush your head? I'm not that big, right? Would not be comfortable, but I'm not going to crush your head. But what I'll do now is kind of sick, but I'll go get one of my wife's high heels, and then I'll step on your head with one of the high heels. Just the heel. Just one heel. Right on your head. Did my mass change? Did the acceleration due to gravity change? But you're going to feel an awful lot of pressure under that little heel, right? So what's different about those two scenarios? Has to do with the area, right? So pressure or stress is a force applied over an area. So if you make the area really small, like under a high heel, what does that do to the stress? Jacks it right up, right? What do we measure area in terms of units? Meters squared, okay? Some sort of squared distance. What's your unit of stress going to be? What units would you have on that? So it's force, right? So you've got this kilogram meter per second squared, right? And then you're going to divide that by meters squared, correct? 1 meter cancels out of the top, 1 meter cancels out of the bottom, and you end up with, you can either talk about it as a Newton over a meter squared, that's an easy way to do it. If you actually want the individual MKS units out of it, it's kilogram over meter second squared. It looks a lot like a Newton, right? Difference between the two is for a Newton, the meter is in the numerator, and for stress, meter is in the denominator. This unit is called a Pascal. A unit of pressure or stress is Pascal. Unit of force is a Newton. Screen. Okay. You guys got force, right? The more massive, the more force you have. The greater the acceleration, the more force you have. The smaller the surface area, the more stress you have, or pressure. Clear on this? Okay. We're going to need these terms for what we're going to talk about later. We're going to get to viscosity. All of these terms play into viscosity, okay? Okay, we said when we stress something, when we put pressure under something, it can deform. How do we measure how something is deformed? That's tough, right? It can deform in a number of ways. Well, engineers have come up with a really simple definition for deformation. It's called strain. It's change in length over original length. All right, this eraser I have up here is about 1 foot long, right? Let's say I put it under tension, start pulling on it. And after I'm done pulling on it, it's 13 inches long. Did I deform it? How much did I deform it? What was its original length? 12 inches, right? Its final length was 13. What's the change in length, or delta L? 1 inch, right? 1 inch is the change in length. The original length was 12 inches, right? 1 inch over 12 inches. What unit do we have? If you have unit, what's the unit for delta L? Inches, right? What about for L? Inches. They cancel out, right? What's the unit? You guys, every time some scientists ask you what you're expected to have a unit, right? This is one of those things where it doesn't have a unit. It's what we call dimensionless. There's no units. The units cancel out. And that might seem confusing, but it's really not. Just think of it as a fraction or a percent. This next example, I think, clear it up for you. So let's say we have a meter-long rod, just like I had with this eraser thing, but we'll make it a meter. Math works out really nice in this case. And I put it under tension, like I show here. And when I'm done, it's 1.1 meters long. What's the change in length? 0.1 meters. What's the original length? 1 meter. What's the strain? 0.1 meter divided by 1 meter is 0.1. 0.1 is the same as 10%, right? So it's stretched by 10%, or it's stretched by 0.1. So I like to think of it in terms of a percentage. That way you sort of have a unit. Or you could just leave it in fractional form and it's stretched by 0.1. Same as 10%. So this little epsilon we have here, that's our typical symbol for strain. You're going to see that a lot. Get used to it. All right, everybody got strain? It's really simple. It's actually really simple. Change in length over original length, and you think about it as a fraction or a percent. Okay. Strain rate. Now this is really important when we talk about fluids. Let's say I've got this little slope right here, right? I put a little drop of water right here. Right next to it, I put a drop of tar. Where are both of those fluids going to end up eventually? End up down here, right? They're eventually going to strain the same. They're going to move the same amount, right? What's different about the movement? Water's going to move a lot faster. Its strain rate is going to be much higher. So you can see already that strain rate is going to relate to viscosity. Water has a lower viscosity, so its strain rate is going to be higher. That's how we actually define viscosity, as you'll see in a minute. It's related to the strain rate. What is strain rate? It's the strain divided by time. And we give it this unit of epsilon with a little dot over the top of it. strain rate, how fast it deforms. This is kind of strange though. What's the unit on strain rate? Per second? What per second? You're exactly right. The unit is per second. You're always used to like meter per second, right? Or feet per second, or something per second. This is just per second. Think of it as percent per second. How much did it change its length in percent every second? If that makes it easier. So yeah, the unit is weird. It's per second. I like to think of it as fraction per second. It's strained by 0.1 per second, or percent per second. It's strained by 10% per second. So strain rate, that's how fast the fluid deforms. Low viscosity fluids deform really fast. They have high strain rates. Very viscous materials deform very slow. They have very slow strain rates. Okay. Ready for some more? I'll bring this all back to lavas here pretty soon. Give you an example first. We have a rock, put it under tension. We stretch it from 2 to 2.4 meters, and it takes 20 seconds to do that. Calculate the strain rate. You can probably do this in your head. Easier with a calculator. Am I getting an answer? 0.01 per second. Where did we get that from? All right, what's strain? Strain is change in length over original length. What's the change in length? 0.4 meters. Original length, 2 meters. What's the strain? 0.2. 20%. But it takes 20 seconds, right, to do that. So every second you're straining by 1%, 0.01, 0.01, 0.02, 0.4. So your strain rate is your strain divided by time. Your strain is change in length over original length. 0.4 meters over 2 meters is 0.2. Units cancel out, meters go away. 0.2 divided by 20, 0.1 per second, 1% per second. Okay. If you have problems with any of these, give me a holler. I'll walk you through them again. I want to make sure everybody has this before we get too far along. All right. Now that you know what pressure is, we're going to talk about how different Earth environments actually create pressure. Where does pressure come from? Well, we have something called hydrostatic pressure. What is hydro? Water. Static means kind of a not moving body. So hydrostatic pressure is the pressure of being buried underwater. Pressure from burial beneath a water column. What's lithostatic pressure? Lithos means rock. So this is the pressure of being buried under rock or soil. And then because you're in volcanology, we have this cool thing called magmastatic pressure. That'd be the coolest way to be buried, being buried under magma. pressure at the base of a magma column. All right, let's say in a few weeks we do a test in here, and we will. I don't know when yet. We will. And if you do really horrible, I'm going to want to bury you in my backyard. It's a reasonable response, right? All right, so let's say I dig a hole in my backyard 3 feet deep. Throw you in it, and then bury you under 3 feet of soil. You going to be under pressure? It's going to be enough to like squish you to death. You'll eventually suffocate, but you're not going to get squished to death. It's just going to be heavy, right? What if I dug that hole 10 feet deep? Be under a lot more pressure, right? So what factors affect pressure of burial? Well, one obviously is the depth, right? The deeper you are, all other things being equal, the more pressure you're going to be under. What else would affect how much pressure you get from being buried? Not just the depth. What else?
The volume of the thing you're buried under.
You're really close. All right, so I put you in that 10-foot deep hole, right? I have two options. I can throw more dirt on you, or I can throw those styrofoam popcorn peanuts on you. What if I buried you under styrofoam? No big deal, right? What if I buried you under ball bearings? So what's different about styrofoam peanuts and ball bearings? The density. The density material has a huge effect on being buried. You want to be buried under styrofoam, not under metal, right? Okay, so we have the depth and we have the density. What else? What's actually creating the pressure on you? The gravity, right? Now, if I brought you to Mars, where we said earlier the acceleration due to gravity is only 3.3 meters per second, or roughly a third that here on Earth, it's not going to be pulling you down with the same amount of force, right? So the three things that affect burial are depth, which you measure in meters, density, which is mass per unit volume, in this case kilograms per meter cubed, and then gravity, which we measure in meters per second squared. Do me a favor, multiply depth times density times gravity and see what you get for a unit. What'd you get for a unit? What does that look like? Look back in your notes a little bit. You've seen that already. It's Pascal, right? What is a Pascal? It's a unit of pressure or stress. So that's exactly how we measure pressure in the earth, is we simply multiply depth times density times gravity. It's just kind of neat. All works out. No constants, no fudge factors, just straightforward multiply these babies together and you get pressure. Here on Earth, G, or gravity, is always going to be 9.8 meters per second squared. If you're on a different planet, you got to adjust. The depth is something you measure. Density is something you measure. Now, geologists and engineers have measured the densities of lots of things. Water's fantastic because it's nice and easy. It's 1,000 kilograms per meter cubed. So think about that. How big is a cubic meter? Meter by meter by meter, right? Not overly huge. So if you had a meter by meter by meter filled with water, what would it weigh on Earth in pounds? Might not know the conversion, 2.2 pounds per kilogram. 2,200 pounds. It's over a ton. Doesn't seem like it, right? I mean, cubic meter isn't that big, but it weighs a ton if it's water. And water is pretty light compared to rock. Sedimentary rocks are about 2,000 kilograms per cubic meter. So if you had a slab of sandstone that was a cubic meter, it would weigh over 2 tons, 4,400 pounds. And if you had an igneous rock, it'd be 2.5 to 3 times. So you're looking at 6.5 or 3.5 tons. Just for that little square. So when you see boulders out there that, you know, good size, you're not moving them easily. They're tons, many tons. All right, here you go. Here's just a quick problem for you to go through. What's the magmastatic pressure at the bottom of a 3-kilometer magma column on Mars? We're going to assume that the magmas have a density of 3,000 kilograms per cubic meter. Remember, the gravity on Mars is 3.3. Now remember, to get your units right, I gave you 0.3 kilometers. You might have to change the unit on that. I think I did my math right. Multiply this out, 2.97 times 10 to the 6 pascals. So we have a nice quantitative way of figuring out the stress or pressure at the bottom of a magma body. Now if that was water instead of magma, it'd be 1/3 of this, or about 1 times 10 to the 6th. Any questions on that? Okay, so we have pressure, stress, same thing. Force is mass times acceleration. Pressure is force divided by area. Strain is change in length over original length. Strain rate is the strain divided by time. And then we talked about ways of generating pressure from burial, which is mass in terms of density in this case. So density times depth times gravity. So how much magmastatic stress if you were buried under an equal depth of igneous, in this case magma on Earth? What's the only thing that's going to change? Depth is the same. You don't change the density. You would just change the gravity to 9.8. So it's going to be roughly 3 times higher. 8.8-ish times 10 to the 6th. Okay, any questions? Hopefully now you've all had your physics either repeat, brand new, but my guess is things like strain might be new to you, strain rate might be new to you. I'm not sure if you covered any of that in structural or not, if you've had structure. No, I don't want to start this. This will take a little while, so I'll save this for next class. So we're going to talk about how fluids move next class, okay? So have a good week. Go catch the game. See you guys all in a week.